Now let's see what are inner products and dot products. Or dot products. You have a fair idea what they are. I'll just define them here. So let x comma y belongs to Rn and x not equal to 0, not equal to y. The inner product is written as x dot y or x transpose y, and it is given as sigma of 1 to n xi into yi. Sum of this. This can also be written as x1 y1 plus x2 y2 plus dot 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 xn yn. This is what is equal to, and it also equals to x norm of x by into norm of y into cos theta. Theta is equal to angle between x and y. This is what dot product means. Some identities related to dot products is x transpose x. The dot product with something is just norm square. Second property is x transpose y equal to y transpose x. This is fairly obvious. If you write this into the formula, it is same exactly. And then the absolute value of the dot product is always less than or equal to norm of x or norm of y. You can see this by this relation, as cos theta's value is always between 0 and 1. So this is true. This result is called Cauchy-Schwarz, SSWA, Schwarz inequality. This relation is called Cauchy-Schwarz inequality. Okay. Now, from inner product and dot product, let's come to orthogonality. Let's come to orthogonality. So what is orthogonality? Orthogonal is related to perpendicular. Most of you also might be knowing about this. I'll just write its a definition. So let x comma y belongs to Rn. Then x and y are said to be orthogonal or perpendicular if x transpose y equal to 0. That is, their dot product is 0. Then they are called, those two vectors are called orthogonals. Even spaces or subspaces can be orthogonal. So what does that mean? So let's say two subspaces S and T of some vector space Rn are orthogonal if every vector x belongs to S is orthogonal to every vector y belongs to this has to be every vector S. So basically all the vectors is S are perpendicular to all the vector in T. So that's what it means. So let's see an example of this. in R square. So let's say this is R square. And this is one of the subspaces of R square. I say this is one of the subspaces of R square. So another subspace which goes perpendicular to this line, to this subspace, is so if this is S and this is T, then S and T are orthogonal subspaces. You can see that any vector in T is perpendicular to any vector in S, and vice versa. Any vector in S is perpendicular to any vector in T. These are orthogonal subspaces. Now let's move on. Related to this, I have a question for you in R3. So let S and T be subspaces in R cube, and both of them are planes. So as we learned that subspaces in R cube pass through origin, and both of these are planes. Can they be orthogonal? Can they be orthogonal? This is the question. So if you want to think, you can pause the video here and then think about it. Yeah. So the answer to this question is no. Two planes in R cube can never be orthogonal subspaces. This is because, so you might think that if there is a plane passing through origin, a plane perpendicular it might be the orthogonal plane. But think about the vectors which lie along the line of intersection of those planes. They are not perpendicular to each other. And there are many other, that is not the only set of vectors which are not perpendicular. There are several other vectors which are not. But so let me show it with a diagram. So let's say this is one of the planes passing through the origin. Let's say this is another plane passing through the origin such that they are perpendicular. And this might be the line of their intersection. Let's say this be the line of their intersection. This dotted line. Then the vectors on this line lie on both of these planes, but they're not perpendicular to each other. So hence, as it turns out, if there is a subspace S which is a plane, in R3, then its orthogonal subspace has to be at least a line. And that line is the perpendicular line to the plane. The line which is perpendicular to the plane is the orthogonal subspace, at least. So this is the think about this. We'll move to the next definition, which is called orthogonal complement, which is very closely related to orthogonal subspaces. So orthogonal complement. So let's say, so let me write the definition and then I'll explain you. So given a subspace S of Rn, the space of all the vectors orthogonal to S is called orthogonal complement. So this means that let's say I have a subspace S, and it will have a set of vectors which are orthogonal to this subspace. A set which contains all these vectors is orthogonal complement of S. So let's see in R2. Let's say this is a subspace S that we are talking about, and this we are in R square, R2. What is the orthogonal complement of this subspace? So all the vectors. So what are the vectors which are perpendicular to this? This is perpendicular. This is perpendicular. This is perpendicular. This is perpendicular. A set of all these vectors will be a line which is perpendicular to S and passes through origin. So this is orthogonal complement. T is orthogonal complement of S. Let's look at the example in R3. So let's say I'll not draw the coordinates. This is R3 space, let's say, and this is the origin. So what will be the orthogonal complement of this plane passing? This is the subspace, infinite plane passing through the origin. This is the subspace of R3. What is an orthogonal complement of this subspace? It turns out the line passing through origin and perpendicular to the plane is orthogonal complement of this. So let's say this is S. Here T is orthogonal complement of S. So these are the two examples. Now let's look at mutual orthogonality and orthonormal vectors. So first we'll look at mutual orthogonality. So just by name it suggests that a set of vectors which are mutually orthogonal. So that's what we'll write. So vectors x1, x2, xk belonging to Rn are mutually orthogonal if xi transpose xj or the dot product is 0 for all I comma j. For I comma not equal to j. So if this happens, then they are perpendicular to each other. They are orthogonal to each other, and this set is called orthogonal mutual orthogonality. This is called mutually. They are mutually orthogonal to each other, and it's like fairly standard stuff. And then we'll define orthonormal vectors. So normal means normalized. So here you by normal you think normalized, not normal as in perpendicular. Normal you should think normalized. So these are mutually orthogonal vectors whose individual norms are 1. So vectors x1, x2, xk which are mutually orthogonal and for all I equal to 1. Okay. So then this set is called orthonormal. That is, each vector has some direction and its magnitude has been normalized. Okay, that's what this means. Now there is an important result or theorem, I would say, which says that if a set of vectors are mutually orthogonal, then they are also linearly independent. So if x1, xk, x2, xk are mutually orthogonal and xi not equal to 0 for all I, so basically none of them are 0, then they are linearly independent. This is a very important result. You might feel that this is very obvious, but let's prove it. Let's prove this result. Let's say a set of vectors are mutually orthogonal. Let's x1 and x2 are orthogonal, are mutually orthogonal. Then if we prove that alpha 1 x1 plus alpha 2 x2 plus alpha n alpha k xk equal to 0 implies alpha I equal to 0 for all I equal to 1 to k. If we prove this, then we have proved that if we assuming this, if we prove this, we will prove the above statement. So let's assume alpha 1 x1 plus alpha 2 x2 and alpha k xk equal to 0, and x1 are also mutually orthogonal. Now we make a dot product with x1, alpha 1 x1 on both sides, alpha 2 x2, alpha k xk, dot product with x1 equal to 0. As it is mutually orthogonal to all the others, we'll be like alpha x1 dot x1 plus alpha 2 x2 dot x1 alpha k xk dot x1. Because they are mutually orthogonal, will remain by alpha 1 x1 to 0. As x1 is non-zero, implies alpha 1 equal to 0. We can repeat this for all xi, and we'll get that x1, x2, xk equal to 0. All of them are 0. So we proved that if alpha 1 x1 alpha 2 x2 dot alpha k xk is 0, then and x1 to xk are mutually orthogonal, then it means that alpha 1 alpha 2 and alpha till alpha k are all 0. This means the above statement is true. All mutually orthogonal set of vectors are linearly independent. Now we come to orthogonal basis, orthonormal basis. What are orthonormal? basis. One of the very common orthonormal basis, before giving you the definition, let me give you an example that we all work with is I hat, j hat, I hat, j hat, and k hat. So these are basis vectors, and they are also uh, orthogonal to each other, and normal, their magnitude is 1. So normal means magnitude is 1. Ortho means they are perpendicular to each other, and basis is that they're linearly independent and they span the whole space. That's what this means. So whatever I told you, I'll write it down. Suppose x1 and x2 are orthonormal, which means they are perpendicular to each other and their magnitudes, individual magnitudes are 1. So given any vector x, we can write as x transpose x1 and they are also x1 and x2 are also span the whole space, whole vector space. Any vector s belonging to S, we can write x transpose x1. Yes. So what does this mean is this is component on x1 times x1 direction and component on x2 times x2 direction. That's what it's saying. This is how we can write x. So x can be represented like this. Any x can be represented like this. But for representing like this, we'll require orthonormality of x1 and x2. So let's just look at it in the terms of diagram. Let's say this is x1, x2. Their magnitude is 1 and they are perpendicular to each other. Then let's say any x transpose x1 and x transpose x2 times x2. This is where you can write it. Now, for writing this, we require orthonormality, that x1 and x2 should be orthonormal. But what if we don't have an orthonormal set of vectors? How do we generate an orthonormal set of vectors when someone has given us a basis? So let's say we have some basis of set A. How can we convert it into orthonormal basis? So that is the question that we ask. So how to produce an orthonormal basis starting with a given basis. So next to xn. Let's say you have in Rn you have been given n linearly independent vectors x1 to xn, and they form the basis of the set Rn. How can you convert them into a orthonormal basis? Because it's, why do we want to convert? Because it is very easy to write uh, any vector x in terms of orthonormal basis. So the way we do it is and we follow a procedure called Schmidt procedure. So we'll try to follow it step by step. So we will do it for an example in R cube. So let R3, so x1, x2, and x3 belongs to R3 be a basis. So they are linearly independent and they span R, R3. Okay. What we have to do is we have to find y1, y2 and y3 which are orthonormal bases. How do we do it? So it turns out that the first y1 you can assume x1 upon mod x1. So let's say you have some x1. So y1 you assume that you make the first vector as convert it into unit vector and give that as y1 itself. So this is equal to x1 by mod x1. Now, if you see, let's say we want to find the second orthonormal vector in the basis. So let's say this is x1. We already found that. Let me use some other color. Let's say this is x1. Let's say this is x2. We already found y1. Okay. Now we have to find a vector y2. So y2 will be in some of the direction, perpendicular direction of y1, somewhere in that plane. Okay. So how can we find perpendicular? So one thing we can do is we can take a component of this along y1 and subtract that. So basically, let's say right z2 equal to x2 minus x2 transpose y1 y1. So what we are doing, this is x2 transpose y1, the component of x2 on y1. This is one, and we are subtracting it. Here we are getting x z2, and then y2 can be written as z2 upon z2 norm. So this normalizes the vector and this gives you perpendicular. We can also see if this is perpendicular to y1 or not. If this is perpendicular to y1 or not, we can take a dot product y1 transpose z, z2, which will give us y1 transpose x2 minus, this is a scalar, so x2 transpose y1, y1 transpose y1. So y1 transpose y1 will be 1. So it will become y1 transpose x2 minus x2 transpose y1. We saw earlier in properties of dot product, we can write it as x2 transpose y1 minus x2 transpose y1, which is 0. So it is indeed y1 transpose z2 is 0, which means y1 and z2 are perpendicular. So y2 is perpendicular to y1. Similarly, so I'll just box it so that you know how to find it. In the third way, we can follow a similar thing. Like we take x3, we subtract this component on y1, x3 transpose y1, y1, and we also subtract its component from y2, x3 transpose y2, y2. So this in turn will be perpendicular to both y1 and y2, and y3 can be written as y3 z3 upon z3 norm. So this is normalizing. So in this way, if we have any three linearly independent vectors in R3, x1, x2, x3, we can find y1, y2, y3 with this procedure, and we can use this procedure to find orthonormal basis in any vector space of R to the power n. So that's the end of orthogonality. Now we'll look at we'll give you a brief introduction of what matrix is. I think most of you understand what matrices are. Um, uh, we will give you a brief introduction of what matrices, and I think most of you understand what matrices are. So I'll not go deep into the basic details. I'll explain you the most important aspects of matrix only. But we'll give an overview of what are all the things in matrix there are. So matrix. Uh, so uh, so it's a there are several columns. So it's a bunch of collection of column vectors, and it generally belongs to m cross n. It can have m cross n means m rows and columns. Then there is something called diagonal matrix, in which only diagonal elements are are non-zero, and rest of them are zero. We represent it by like this. Then we have something called upper triangular matrix, which means diagonals and above diagonal elements are non-zero, rest of them are zero. We also have something called lower diagonal matrix, which is similar to upper diagonal matrix, that is diagonal and elements uh, lower two diagonals are non-zero and rest of them are zero. There's something called identity matrix, in which diagonal elements are all one, rest of them are zero. Uh, there's something called, so let's say if there is a matrix A and it's non-singular, which means it's there's something called determinant of A, which you all know, and I'm not going to explain it much, but you know what it means. So there is something called determinant. If it is non-zero, then A inverse exists. What does this mean is A inverse and A is equal to A inverse to I. This is the property of A inverse or something. So also there's something called rank of a matrix. So I'll explain this in a little bit detail. So let's say I have an example 2, 4, 3, 1. Or let's say I'll take one more column 5, 2. So there is something called column rank, which is the dimension of the dimension which the column space or the column vector span. Okay, so let's say 2, 4, 2, 4, 3, 1, 5, 2. Let me first write the definition. So dimension of column vectors. So the column vector spans some subspace or space. The dimension of that subspace is actually the column rank. There's something called row rank. Similarly, dimension of row vectors. So row vector spans some subspace, and the dimension of that subspace is called a row rank. So let's see what is the dimension of the column vector. So 2, 4, 3, 1, 5, 2. 2, 4 is some vector like this. 3, 1 is some vector like this. And 5, 2, some vector like this. It turns out this span R square. They, even though they are not linearly dependent, but they span R square. Their dimension is 2. And what is the row rank? So let's see. So what are the row vectors? So I'll not so 2, 3, 5 is 2, 3, 5. Okay. And 4, 1, 2 is 4, 1. So any two vectors in R3 always form a plane. So they span a plane. So dimension of, so basically it's the dimension of that plane is 2. So row rank and column rank both are 2 here. Is this a special case or does this always happen? It turns out row rank is equal to column rank always. This is true for all metrics. So, and hence this is some called rank of a matrix. Okay. Now transpose of a matrix. There is something called transpose. Basically A transpose. So let's say A is some 1, 2, 3, 4 matrix. Then A transpose is just reversal of their rows and columns. 3, 2, 4. Okay. So determinant we have already talked about. Then orthogonal matrices. So orthogonal matrices have a all the matrices which follow this property A inverse equal to A transpose. That is, their transpose is itself their inverse is itself their transpose. So for example, let's take a 2 cross 2 matrix. 1 by root 2 and 1 by root 2 and minus 1 by root 2 and 1 by root 2. So if you transpose this and multiply with itself, you'll find that it will give you identity matrix, and this is a orthogonal matrix. Let's try to do it. 1 by root 2 I'll take out common. 1 minus 1 1 and I'll multiply with it with A transpose. Let's say A transpose will be again 1 minus 1 1 1 1 by root 2. So it is 1 plus 1 0 0 1 plus 1. And 1 by root 2 1 by root 2 multiply we give 1 2. So it becomes 2 by 2 0 0 2 by 2 2 1 0 0 1. So basically it's transpose its inverse itself. So these are called orthogonal matrices. You can have R3 cross 3 also in that. In any Rn cross n, you can have orthogonal matrices. Now let's talk about eigenvectors and eigenvalues and eigenvectors of a matrix. What are the eigenvectors and eigenvalues? So for any square matrix A, so we'll present it Rn cross n. Eigenvectors and eigenvalues. Eigenvalues are the scalars and eigenvectors are the vectors. And eigenvalues can be both real and or complex, are given by this. So which satisfy this equation. So eigenvalue. This is eigenvector. So lambda belongs to complex plane. It can be a complex number or a real number. And x belongs to R n cross. So it's a n cross 1 vector. So notice these two are same. So if a real number and a vector satisfy this equation, they are the pair of eigenvalue and eigenvectors. How do we find these eigenvalues and eigenvectors? So we bring ax minus lambda x on the left hand side. We 0. So for this to have a non-trivial solution, the determinant of a minus lambda should have to be 0. So this is called the characteristic equation of A. And you'll get a polynomial equation in this, and the roots of those equations are the eigenvalues. And the corresponding eigenvectors you can find now putting back those roots in this equation, and those vectors are corresponding eigenvectors. So most of you must have done this in courses. And one more thing, these are n roots. So I'll not do an example here, but I hope you understand this. Now let's come to symmetric matrices. These are very important for this course because we'll mostly be dealing with symmetric positive definite matrices, and it's better to know some of the properties of these matrices. So I'll write them out here. So what is a symmetric matrix? It's a square matrix such that A transpose is equal to A. So if you transpose the matrix, you will get the same matrix. So it turns out that it has a structure. So it has diagonal elements, but every ith jth term is same as jth ith term. So these are same. You take some other term. Kth pth term is equal to pth kth term also. So there is a structure in symmetric matrices, which I'm sure you are aware of. Then we'll write some properties. Symmetric matrices. So if S is symmetric, it turns out that sorry, I should write A. A has all real eigenvalues. All the n eigenvalues that A has are real. They are not. They do not have the imaginary component. They are all real. Corresponding eigenvectors are orthogonal to each other, are mutually orthogonal. So So all the eigenvectors are usually orthogonal, and they can be chosen to be orthonormal. I.e., that you find some vectors and just divide them by their norms, you'll get the get the orthonormal set of eigenvectors. Also, if you make a matrix S such that uh, all the uh, 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 eigenvectors are there as a column vectors of S, like this, then S is orthogonal matrix. This is orthogonal matrix, which means S inverse is equal to S transpose. It turns out that it will be orthogonal matrix. And one last property, which is one of the most important property, if you use this S like this, S transpose A S, where A is symmetric and S is its corresponding eigenvector matrix, which is normalized eigenvectors matrix, then you'll get a diagonal matrix whose diagonal elements are eigenvalues. This is the story. These are very important properties. There are various proofs given. You can look up the linear algebra book that I have shared with you, or I have told the name to you. But these you can look the proofs there. But these are fairly important properties, and we'll be using them quite a lot in this course. So moving ahead from symmetric matrices to quadratic form. What is a quadratic form? So for that to happen, let's assume let A belongs to R n cross n. So A B and A transpose is equal to A. So let A be symmetric. So what does and let Fx equal to X transpose A X, where X is some vector in Rn. Then it can be said that Fx is purely quadratic. Which means, what does this mean? Let's see it with an example. So let's say A is equal to a symmetric matrix 1, 2, 3, and 3. And let's say what X transpose A X means. So it means X1, X2, 1, 3, 3, 3, X1, X2, which means X1, X2, X1 plus 3X2 and 3X1 plus 2X2. And if further multiply, we'll get a scalar, and x1 square plus 3x1 x2 plus 3x1 x2 plus 2x2 square, which means x1 square plus 6x1 x2 plus 2x2 square. So you can see every term in this is a quadratic term. There are no single power term, no zero power term. So that's what it means, that if X A is symmetric and X transpose AX is purely quadratic. That's what it means by being purely quadratic. Now we'll define a few terms through a table because all of those terms are almost the same. So A is, you might have heard of these terms, positive definite uh, if x transpose Ax is greater than 0 for all x to Rn, except 0 obviously. So if at 0 this is 0, right? So other than 0, if other vector we take from Rn and we put it here, and if that value is greater than 0 always, then we called a positive definite matrix. We call it positive semi-definite if x transpose Ax greater than or equal to 0 for all x belonging to Rn. So at 0 it is anyway 0, but it can be 0 at some other vectors also. Then, but it should not be negative. So it's not x transpose Ax should never be negative for all the vectors in the real Rn space. It is called negative definite if x transpose X less than 0 for all x belonging to Rn. So it's same as positive, but x transpose Ax is purely negative for all vectors except 0. So similarly, we can also define negative semi-definite. So negative semi-definite means x transpose Ax is less than or equal to 0 for all x belonging to Rn. So this is what negative semi-definite. There is one more category called indefinite. So which means x transpose Ax can be both is zero for some, is positive for some x and negative for some x. So A is neither, basically A is neither uh, positive definite nor negative definite. Then it's called indefinite. So for some x's, x transpose Ax is positive. For some x's, x transpose Ax is negative. Then it is indefinite. So these are definition. But how do we check that whether A is a positive definite matrix or not? Because for large order matrices, it's very difficult to check this condition. It's very difficult to check this condition. So how do we numerically check whether a matrix A is positive definite or not? So how to numerically check if A is positive definite? So it turns out that I'll share some results with you. A is, we'll have the same tabular format. Positive definite if it turns out that these are related to their eigenvalues. So if and only if eigenvalues of A are all positive, all the eigenvalues of A are positive, then it is positive definite. It's positive semi-definite if eigenvalues are positive or 0, either positive or 0. It's negative definite if all eigenvalues are negative. and it's negative semi-definite if negative or zeros. And if we talk about indefinite, eigenvalues are both positive and negative. That's what it is. So both positive and negative. And it turns out that for us, positive definite is a very important matrix. So we have to continuously, we have to check whether a given matrix, symmetric matrix, is positive definite or not, because if it is positive definite, we have some conditions that we can use. Apart from these checks, there are some other numerical checks as well, with which we can check whether a matrix or symmetric matrix is positive definite or not. I'll list them out. I'll not tell you it in detail because they are fairly simple, but it's good to know about them. So some other ways of checking positive definiteness. So first is Sylvester criterion. This means it says A is positive definite if all its principal minors are positive. So what is a principal minor? You actually know about it. I'll just show it to you with an example. So let's say this is a matrix. The same matrix I'll write 3 times because it has 3 principal minors. So it turns out that first principal minor is A. Second principal minor is determinant of A, B, D, E. And third principal minor is the determinant of the whole matrix. If all these 3 are positive, then A is a positive definite. That is Sylvester criterion. Now there is other criterion called Cholesky decomposition. So A is positive definite if there exists a lower triangular matrix L with positive diagonal components such that A is equal to N transpose. So if A can be, we can find some lower triangular matrix A, and as it turned out that L transpose will be an upper triangular matrix. So such that their product is equal to A. Then this is called Cholesky decomposition. And if we can find such an L with positive diagonal components, then we can say that A is positive definite. And this decomposition is called Cholesky decomposition. Now we arrive at the final problem of a linear algebra that we try to solve, and that is solution of Ax is equal to B. So for optimization this is a broad topic and it is taught very detailed in linear algebra courses. For us, in optimization problems, mostly A is positive, symmetric and positive definite. So if A is symmetric and positive definite. So how can you find the solution? So one very obvious way to find the solution is Ax is equal to B implies X star or the solution is equal to A inverse of B. Because it's symmetric and positive definite, then we can find A inverse always. This is one method, but this is computationally expensive. Very computationally expensive. So we generally don't do this in computers at least. So finding A inverse is very costly. So another method is, as we saw it, Cholesky decomposition. So as A is a symmetric positive definite matrix, so we can always find a matrix L such that we can decompose A into L and L transpose. Then equation Ax is equal to B becomes L transpose X equal to B. Now we assume this to be Y. I let L transpose X equal to Y. This is equation, and L Y equal to B. Okay, so we first solve equation 2. So Ly equal to B. So the thing is, this is easier to solve because we can solve it using forward substitution. Because L is a lower triangular matrix, we can use a method called forward substitution to find Y. So let's try to see what forward substitution is. So let's take a simpler example. This. So you can see that forward substitution is x1 equal to 4. Let's change this value to 5. 5x1 equal to 4 and 2x1 plus 3x2 equal to 5. So with this you can directly give x1 equal to 4 by 5 and you can put it here and you'll get x2 equal to 5 minus 2x1 divided by 3. So it turns out if it is a very big matrix, you can just keep on finding S1, put it in x2's equation to find x2, and then do simultaneously and just go one step down to find the next variable. This way, it's easy to solve this equation and it's less computationally expensive than finding A inverse. Once you solve this, you find Y, and then you can solve the second equation. So once you find Y, you can solve this L transpose X equal to Y. Now this is an upper triangular matrix. And you can use what is called a back substitution. So instead of starting from x1 and then going on to xn, you can start from xn and go back to x1 to find the solution. And it is still computationally inexpensive because you're not finding any A inverse. So in this way, you can solve Ax is equal to B, and hence we'll have to solve a lot of Ax equal to B linear equations in optimization, and this is the method we'll generally use to solve those equations. So this is the end of set theory and preliminaries of linear algebra. Uh, Till this, I'll end the lecture. In the next lecture, we'll try to understand the analysis and the calculus required for the optimization course. And we'll also look of what are the next topics like optimization in one variable. So we will also start that. So this is the end of the lecture. If you have any question, let me know. Thank you.